Hello everyone, welcome again to the MathCAD tutorial sessions. Today we're going to talk about symbolic operations and numerical techniques in our lesson number 4 of MathCAD. And let's start talking about symbolic operations. And symbolic operations is a feature that is included in MathCAD, which is undeniably the most powerful feature of MathCAD. Not necessarily in its applicability, but, well, which is an understatement, but the symbolic operations is probably the smartest of all features in MathCAD. It's actually very difficult from a software point of view to be able to perform symbolic manipulation and symbolic operations. And in some instances that we're going to exercise today, it's not going to be so apparent, but it's going to be obvious when we try to do, for example, calculus-based symbolic manipulation, where you can very easily see how complicated this will be from the software standpoint, and how smart this software is to be able to do this kind of things. It's perhaps the closest a software package to an end user would be to artificial intelligence, because it has to actually make some very difficult decisions when providing us a response to a symbolic analysis, symbolic manipulation, or operations. So MathCAD includes symbolic operators that allow for a number of algebraic manipulations to be performed. That includes factorizing, simplifying, expanding, collecting, performing series expansions, integrating, differentiating, inverting functions, and performing even matrix manipulation in symbolic form. So we're going to exercise some of these today, and you're going to be able to see right away how impressive this is, and how useful can it be in the long run. So the symbolic toolbar below provides a list of the available operators. You can open there's actually shortcuts for most of these operations, for most of these symbolic operations, but you can actually access them directly through a toolbar. So let's start by opening MathCAD and opening that toolbar. And this is the toolbar that we are going to employ, or that I like to employ, to actually navigate through these symbolic operations. And mine's are already open, but I'm going to close them. And we've used the programming toolbar and the Boolean toolbar in the past, as well as the Greek toolbar. But let's open up the symbolic manipulation toolbar, which is indicated in the general toolbar here with a little cap. And you can also go to the View menu, Toolbars, and open the symbolic toolbar. And as you can see, is a pretty sizable toolbar that includes many operators, out of which we're going to exercise a lot today. For example, going back to the presentation, the first one of these operations that we are going to exercise is the use of the right arrow, the symbolic evaluation arrow. This is sort of an equal sign, display equal sign, but only for symbolic evaluation. Remember that we've actually used many forms of the equal sign in MathCAD. One is the assignment equal, which is a column equal. The other one is a display equal, to display the result or the value of a variable. That's a regular equal. The other one is a control equal for comparisons. And the other one is the global definition equal, the 3 horizontal bars. Now this is a fifth equal sign, which is called the symbolic evaluation equal, or the symbolic evaluation period. And it would allow you, given an expression on the left-hand side, followed by the symbolic evaluation, it would allow the symbolic engine to start actually searching for possible solutions on these specific operations. So let's perform a very simple operation like the one posted on the presentation, and that would be, for example, if we have an equation that's a symbolic equation, 3a plus 6a, and we don't have a value for a. Okay, a is an undefined variable yet, but we want to perform this very simple operation from the symbolic standpoint. And obviously you're going to be confronted with these situations many times as an engineering student, where you actually solve for things in symbolic format. You don't necessarily have values for the variables. You actually have forms and formulations that you have to arrive at a solution for a specific variable without actually getting a numerical value. So let's say you have an expression, very simple, 3a plus 6a, and we know that the answer for this is 9a. If we want to evaluate this symbolically, all we have to do is select the whole expression and click on the symbolic, which is just Control plus, symbolic evaluation, and there it is. The solution is 9a. Notice that it took a while for MathCAD to spit that solution. I'm going to delete it. I'm going to do it again. You can count as you hit enter. It took, well, now it has it in memory, but it took a couple seconds to get to the solution. Very simple solution, 3a plus 6a. It's not a trivial thing to do for software. Software has to investigate a set of possibilities, go into a database of possible solutions, and analyze that whether this is true numerical evaluation, a possible solution candidate to the expression. And as simple as this one looks, 3a plus 6a, to arrive at that solution took a lot of software development. Okay, so going back to the presentation, a second example is the use of the solve instruction within the Symbolic Operations toolbar. The solve instruction can be used to provide a symbolic answer to a specific equation of a single variable provided on the left-hand side. So let's say that we have an equation like this: ax squared plus bx plus c equals 0, which is the standard quadratic equation. We know the answer for that equation. So we have a times x squared, and notice that it has no coefficients. A is a letter, b is a letter, and c is a letter. We have no numerical values for them in this MathCAD file. They haven't been defined. And now we're going to set this equation equal to 0, not the display equal, not the definition equal, the control equal. Okay, this equation is equal to 0. This is a control equal. Okay, you insert that equal sign with control equal or control plus 0. And now what we're going to do is solve for this equation. Now you can just say solve without specifying the variable that you want to solve for, and MathCAD will try to determine which is the most likely candidate here for a variable to be solved for. You can actually solve for A or solve for B. You can solve for A in terms of X, B, and C, or you can solve for B in terms of A, X, and C, and so on. MathCAD will by default determine which is the most likely candidate for a variable to be solved for. In this case, it doesn't know because there are too many options, so you actually have to specify comma X. Solve for X, and it will provide you with the solution. Now this is a very simple case because we already know the solution to this. So this is a standard quadratic equation. So MathCAD is actually giving you the answer. Notice this is the right answer. It's minus b over 2 plus square root of b squared minus 4ac divided by 2, or the negative of that, minus b over 2 minus so on and so forth. And this is exactly what you know as the quadratic form solution. So as you can see, I gave the solution to you in the form of a vector because there are two possible solutions. So this is how you use the solve operation in Symbolic Manipulator. Next one, you can use MathCAD to expand and to factor and to substitute and simplify. Okay, so let's study those four in the same sequence. You can actually expand, and like in this case I'm showing the multiplication of two binomials, and you can expand in terms of x. You don't really need to specify x in this case because x is the only symbol. Everything else is a number in this case. But if you had specified x minus a and x minus b, you can expand in terms of x, and it will provide you this solution in terms of a and b. So let's say in this case we expand in terms of x. All it's going to do is expand that multiplication of binomials, and it's obviously not limited to this. You can specify an expansion many times more complex than this one in hand. Also, you can use it to factor. If you have a polynomial like that one that we just expanded, that ends up being a quadratic polynomial x squared minus 9x plus 14, you can actually retrieve back this factorization form, factorized form, by using the factor operator, which you can use directly from the menu, or you can use with the Symbolic Manipulator toolbar as factor. You can also substitute. If you had an expression on the left hand side and you say I want to substitute all the x's by y's, then you say evaluate, and this is what you're going to get. Everywhere you had an x, it's going to be substituted by a y. And finally, you can simplify. You can simplify expressions There maybe where a common denominator can be collected, or maybe something that can be factorized, or something that can be operated between numerator and numerator, something that can be canceled out between a numerator and denominator. The simplify expression or the simplify operations will take care of that for you. So let's look at those four expressions, and let's start with the expand. So let's say again we have that multiplication of two binomials, x minus 7 and x minus 2. In this case, we can expand using the symbolic manipulator toolbar, and notice that the evaluator operator is already placed for you, and you can either say comma x or nothing, because in this case x is the only symbol in this expression, so it would actually know to expand in terms of x. You can also say, let me delete this, you can say expand comma x in terms of x, and it will do exactly the same for you. Or you can factor. You can take this expression and try to factor it back to the binomial form, if there is a possibility for that, and actually every quadratic function or cubic function will have a possibility to be factored in terms of binomials. And let's say we'll factor these, and since x is the only symbol in this expression on the left hand side, there's no a's or b's, it would already know how to factor it. Or we can just say factor with respect to x, and it will provide us with the same solution. In this case, there's no ambiguity. It already knows that it's going to factor with respect to x. So let's do this again. Let's add a parenthesis here to make it clearer to read. Factor, and it knows how to factor back into binomials. Notice exactly the same solution that we had expanded on the previous exercise. So we can also substitute, and let's say we had an expression like the one that we had in the presentation. It reads x cubed minus 2 times x squared minus 3 times x plus 4. Just a cubic polynomial. You can have anything. You can have a transcendental function if you want. And then we are going to substitute. Anywhere we see an x should be substituted by y. Notice that the control equal was already inserted there for you, and the evaluation operator was inserted there for you. At the end of the process, it will take every x on the expression on the left and substitute it by a y. And by the way, the expression on the left can actually have as many symbols as you want, as many expressions in terms of symbolic variables as you want, and it would just take the x's and replace them by y. And the last expression that we looked at, or the last operator, is the simplify operator. This one's very powerful because it will allow you to obviously simplify expressions to get redundantly the simplest version of it. So if you had an expression like the one I have in the presentation, a divided by x minus 3 plus b divided by x minus 4. This is actually not a good candidate for simplification. You can attempt on simplifying this, but it will provide you with the same. It seems that that is the most simplified version because it's already separated. This is an expression that will probably be a better candidate to factorize. If you want to combine common denominators, maybe factorization is the option. So I combine the common denominators and then I make the operations on the numerator to reach this expression. But if you had an operation just like this, for example, a divided by the square root of x plus 1 plus x plus 1. This one you can simplify by combining the denominator of the first expression with the numerator of the second one. And notice it just combines it into a single one that is simpler than the original one. A single denominator of square root of x plus 1 and the multiplication through to reach that final expression. So these are apparently very simple operations, but as you can see, every time we hit enter, MathCAD takes a few seconds to actually achieve a solution, and the reason for that is because it's actually very complicated. The software and the decision-making process behind this symbolic operations is very complicated. So another very powerful feature of these symbolic operators is MathCAD ability to handle matrix manipulation. And let's go to the presentation to look at what we have. So in terms of matrix manipulations, you can actually calculate the transpose of a matrix that is given in symbolic format like this one, or maybe the determinant of a matrix that is given in symbolic format. We know that we can calculate transposes and matrices, and determinants and inverses of a matrix if the matrix is given in numerical format. There's no problem with that. But what if the matrix was given in numeric format? And in this case, in symbolic format, in this case, MathCAD is able to do it through the symbolic manipulator. So let's say I give you a matrix, a 3x3 matrix. I hit Control M to insert a matrix, or you can go to the Insert menu and insert a matrix. I have a 3x3 matrix. I'm going to call this matrix A, B, C, D, E, F, G, H, I. Okay, we have a matrix with 9 coefficients, 9 dependent coefficients, and they happen to be given symbolically. Each of these coefficients can mean anything. We don't know. This is just an illustration. And I can actually use any of these 3 commands to calculate the transpose of this matrix, the inverse of this matrix, or the determinant of the matrix. So if I hit transpose, notice that all it did was just switch the rows by the columns. And if this matrix would not have been square, for example, if it was a rectangular matrix, the result would have been a rectangular matrix of opposite dimensions, of course. I can take this matrix again and apply the symbolic operator to calculate the inverse. Second matrix symbolic operator is the inverse. Evaluate, and there it is. There is the inverse of that matrix. It is also a 3x3 matrix with this coefficients. Notice how complicated in terms of this, even if this is a 3x3 matrix, which is a simple matrix, it took a few seconds for MathCAD to give you a solution. It is because it requires a lot of operations to achieve or to reach the form for the inverse of the matrix. Same thing for the determinant. If I give you this original matrix, A, B, C, D, E, F, G, H, I, and let's select the matrix and do the determinant of this matrix, this is the expression that you will get at the end of the day. The determinant of this matrix is given by this combination of the 9 coefficients. Okay, let's go back to the presentation. Now, MathCAD's symbolic integration and differentiation capabilities are, I would say, probably the most powerful ones. Well, besides for some operations that we're not going to get to exercise in this set of tutorial sessions, which include expansion and series and Z transforms and Laplace transform and fast Fourier transforms. So some of those things some of those operations you're gonna get to see at upper level classes, and then you know that they are available in MathCAD for you. But probably at this level you can already relate to differentiation and integration, and you already know how important that is. And MathCAD can actually perform these operations for you in symbolic format, not only in numerical format. Not only MathCAD has the capability of giving you, for example, an integral of an expression from 1 to 2, or from an integral with limits of integration in numerical format. It would also give it to you in symbolic format, and it would also differentiate for you in symbolic format, like in this expression that you see right here. Okay, so let's see the options that we have to perform those type of operations. So let's say I have an expression. Let's say I am going to bring up also the calculus toolbar, which is this one right here. And I'm going to set up next to the symbolic toolbar. And I want to introduce an integral, an indefinite integral, which is obviously an indefinite integral is that one with no limits of integration. That would require obviously a symbolic integral or a symbolic solution. I can either click here or I can say Control I, and it's exactly the same thing. So I want to integrate the expression x squared minus 3x plus 6. And obviously this is a very simple integral because it's a polynomial, and MathCAD should know how to do this very easily. But again, you can never understate the simplicity of these when it's being done symbolically. There's a lot of decision making that takes place for just to do this. And notice how long does it take? 4, 5, 6, 7, 8, 9 seconds to get that simple integral. Okay, because it has to go through many databases and many operations in order to achieve this. Okay, this is the integral of this expression. You can also integrate by just taking the integrand, the function that you're trying to integrate, stepping on a variable that you want to integrate over. X, for example, is the variable you want to integrate over. Make sure not to step over x squared, because that's a completely different variable. You can step out under just a single x without making sure that you don't select the square as part of the integration variable. Select x, go to symbolics, variable, integrate. After you do that, you get exactly the same expression, as you can see. Okay. Now I'm making this example with a very simple polynomial. How about if we had, for instance, a natural log of x, which is an integral that requires integration by parts, for example. Can MathCAD do it? It's a transcendental function, it's a logarithm, it's an integral that requires integration by parts. It did it. X times log of x minus 1, and that's extremely difficult to do from the programming point of view. Let's see another expression, very difficult integral by part. E to the x times sine of x. This is an integral that you have to solve integrating by parts. That would require a couple of integration by parts and then an implicit representation. It actually solved it for you. It's e to the x times the cosine of x minus the sine of x divided by 2. Right? Other types of integrals, control I, let's say a simple sine of x. That should be simple. It should be the minus the cosine of x, and there it is, minus the cosine of x. Now you can do exactly the same differentiating. The difference between, well, differentiating is not as difficult as integrating from the software point of view and from the analytical point of view, because all functions have a differential, have a differentiable form, but not all functions have an integration analytical form. So there are many functions that you can actually, that do not actually have a closed form integral, an analytical symbolic integral. But every function that we can think of has a derivative. So let's say that we want to now differentiate, and for that we use the ddx expression. Make sure not to just type d and divide it by dx. It doesn't work that way. And let's say we want to differentiate the expression, again a polynomial, 3x cubed minus 4 times x squared. Oops, that's not going to be easy. For 4 times x squared plus 2 times x plus 6. And let's see what MathCAD does differentiating this. As you can see, this is a simple example because it's a polynomial. The derivative of 3x cubed is 9x squared, and so see how fast it did it compared to the integration, although both the integral and the derivatives are of polynomials. The other choice is that you just simply write the function, again pick the x, go to symbolics, go to variable, and go to differentiate, and there it is. You got exactly the same expression. Okay. And there it is. Well, this was a polynomial, but can it do it to a transcendental function? Let's see. What is the derivative of the log of x? It's 1 over x. No problem. What is the derivative? Let's see a derivative of a product. Let's see a derivative of a quotient. E to the x divided by the sine of x. Let's see if it can do this. And there it is. There's the first one times the derivative of the second one minus the second one times the derivative of the first divided by the second one squared. And this is already simplified, or actually unsimplified. And if we take this, write it down here, maybe we can just select the whole thing and say simplify this expression. And we found an expression that has a single denominator, which looks a little bit simpler than the first one. So these are the options of the symbolic manipulator, and as you can see, very powerful, and never underestimate the power of these. Although we're just going over very simple examples, it is a very powerful feature of MathCAD that takes a lot of skill to get to where it is. All right, so let's go to the presentation and let's talk about solve blocks. Solve blocks, which by the way can also be done on from the symbolic point of view, are an alternative way to solving system of equations, for example, but is a way that you can use to solve system of equations when those equations are not necessarily linear. Remember that when you have a system of linear equations that have the same number of equations as unknowns, you can always form a matrix and a right hand side vector, and you can get to a solution like we've done with Excel, we've done with MathCAD, with the matrix operations. But let's say that you have a system of equations that doesn't necessarily have the same equations as unknowns. Let's say that it's an overestimated system of equations. Or let's say that you have a system of equations which are not necessarily linear. That you have equations where the unknowns do not appear linearly related to coefficients. You can use a solve block to get through that. So you can use a combination of the given statement and defined statement to get to the solution of a system of equations, and you always need to provide an initial guess when using solve blocks. Okay, so here's one example. Let's say that you want to solve the system of equations. It is important that you don't use the display equal or the assignment equal within the block, within the given find block. You have to use the control equal. So you have the system of equations x, y, and z. Okay, it's a system of 3 equations with 3 unknowns. It seems linear because all the variables are related to coefficients linearly. And it's a system that you can actually easily set up as a matrix vector system, so there's no reason why solve it with a solve block, but just to exercise this, this is what we find. Okay, so let's exercise this. Let's say again that we have a system of equations, and to begin with, we're going to give initial guesses. We have a system of equations where we are interested in solving x, y, z. Whatever x, y, z are, depending on the application. This can be electric potentials, or it can be pressures, or it can be temperatures, or whatever they are. And then you start the block by saying given. As soon as you say given, everything below that statement will be part of a given find block, and it will solve it iteratively. Okay, so let's say the equation or the set of equations are again 2x plus y minus c. Now control equal. Everything within a solve block has to be defined using the control equal. Second equation is 3 times x minus 2 times y plus 2 times z. Again, control equal minus 1. X plus y minus 3z. Control equal 4. And then you close the loop by saying find x, y, and z in parentheses equals, and there's a solution. Let me give a little bit more space. Now, since this is a system of equations, of equal equations with equal unknowns, and all the equations are linear, there's only one solution for these systems. So it doesn't matter what initial guesses I pick. I pick 1,000, I'm always going to get the same. I pick minus 1,000 for C, it doesn't matter. I'm only going to achieve the same exact solution, because systems of equations that are linear, that have the same number of equations that are unknown, have a unique solution. Okay, like in this case, it's just 0.429 minus 0.071, and so on. The other alternative for the system of equations is just to create a matrix, 3 by 3. This matrix is 2, 1, minus 1, 3, minus 2, 2, 1, 1, minus 3. Okay? And then multiply the inverse of that matrix times the right hand side vector, which is a 3 by 1 vector, which is 2, minus 1, and 4. Notice that the coefficients correspond exactly to the coefficients of the system of equations, whatever goes with x, whatever goes with y, and whatever goes with z, in that order. And then if you multiply this 2, you'll get exactly the same solution as we had before. Or you can just name this one A, this one B, and just simply say how much is A to the power minus 1 times B, and there's your solution. Same thing. Or what is the linear solution, L solve, of A comma B? It's exactly the same thing but faster. 0.429. So you see, it doesn't matter what you do, you always get the same solution. Now what if, and by the way, you can also, instead of just displaying the solution of this find block, you can just delete this, and let's say I want the solution in a vector. Oops. I want V, the vector V, to be the solution. It's going to be a vector because this is going to include 3 solutions, or 3 elements of the solution, X, Y, and Z. And then I can just display V, and there's my answer. Okay, it's exactly the same thing. You can display find directly, or you can just retrieve the solution of the find block into a vector. Now, what if you had a system, and let's again start by a set of initial conditions, X, Y, and Z. And now let's define a given block. And now we have a system that looks like x squared plus y squared plus z equals 2. And then the second equation is x plus 2y plus z squared is equal to 1. And then the third equation is x plus y plus e to the z is equal to 3. Now this is a system that has the same number of unknowns as equations. Notice we have x, y, and z as unknowns, and we have 3 constraints, 3 equations, or 3 rules that govern the relationship between these variables. Now what's unique, or as a matter of fact non-unique about the system, is that it's not linear. Okay, you can see that the unknowns x, y, and z are not related to each other through linear combinations, not necessarily just the coefficient times the unknown. We have this one square, for example, this one z is a square, and this one z is even the argument of a transcendental function. That makes the whole system be nonlinear. If at least one of the equations has one of the unknowns be in a nonlinear form, then the whole system is nonlinear. Well, what happens with nonlinear systems? Nonlinear systems may or may not have a solution. If the solution exists, the solution might not be unique. There might be many possible solutions that solve the system. And then what do we do with these? Well, we can actually solve this, not with a matrix vector system, because we cannot form a matrix vector system out of these, because we have a nonlinear combination of terms. We can use the min error. Instead of closing the block with a find, we can close it with a min error, which means minimize the error in the solution of x, y, z. And what do we get? We get this set of x, y, and z solutions. And these is a combination of x, y, z that minimizes the error on all these 3 equations simultaneously. Now, because this is a nonlinear system, there's a possibility that if I change the initial guess, I get a different result. As you can see, if my initial guess was 0 on z, I got 0.998 minus 0.373. But if my initial guess is 10, notice what I get: minus 1.247, minus 1.372, and 2.588. Now, those 2 sets of solutions are completely valid. The thing is that since this system of equations is not linear, then the solution is not unique. Okay, it's very important for us to remember that. Now that's why I use the min error. I could have tried to use the find, but sometimes the find fails to find a solution. In this case, it got it, but it got a completely different one, which is also valid. But sometimes the find, if the system of equation is too nonlinear, it sometimes has a problem on getting to a solution, and a safer way of getting there is using the min error expression. So again, you cannot form a matrix vector system with a system of equations because the system of equations is nonlinear. Same thing can happen if you have more equations than unknowns, or more unknowns than equations. You can always get a solution through minimization of the error, through min error, but not necessarily through the find. Okay, so that brings us to one last topic. We looked at the solved blocks, the possibility of solving system of equations, whether they're linear or nonlinear, with the solved blocks. Okay, systems that are nonlinear. A safer way of getting to the answer is using the min error instead of the find to close the given loop, like in this case. Now, let's look at some numerical techniques. And by numerical techniques, we understand mathematical operations that lead to solutions of linear or nonlinear equations, differentiation, integration, solution of differential equations, transformations, expansions in series, that are done through approximations. Okay, this is a numerical technique. When you hear the word numerical in mathematics or numerical in engineering, is because you use the computer's ability to perform many calculations simultaneously, or many calculations in an iterative fashion, and repeatedly, many simple calculations repeatedly, to actually try to find the solution of a very complicated one. That's a numerical technique. A numerical technique is always usually backed up by an algorithm. An algorithm is a set of instructions that turn a very complicated expression into very many simple expressions. Like, for example, if I give you a differential equation, you probably haven't seen what a differential equation is yet, but you'll see what that is after Calculus 3. A differential equation is just an expression that through differentials it expresses the behavior of a specific system, and is basically a constraint, a set of rules for the behavior of the variable that you're trying to solve. So a differential equation is an equation whose solution is not a number or a set of numbers. The solution of a differential equation is a function, actually. So a single differential equation is usually a very complicated expression, and that complicated expression leads to a solution that is gotten through a very complicated set of steps, usually. Now, we can use numerical techniques through an algorithm to turn the solution of a single differential equation into many solutions of very simple equations, and get a solution at the end as an approximation of the original expression. Okay, so these are numerical techniques. Set of algorithms behind the conversion of a complicated system into very simple ones, that through the use of the computer power for many iterative types of operations will lead us to an approximation of the solution, not necessarily the exact one, but an approximation to the solution. So let's see some examples. Let me show the presentation again. Some examples include the root of a function, the roots of a function, for instance, the roots of a polynomial. This is all done, by the way, through numerical approximations. MathCAD doesn't do this analytically. It doesn't do this through symbolic manipulation. It does it through numerical approximations, iterations. You can calculate integrals and derivatives through numerical approximations as well. So let's see. For instance, if I had an expression like a cubic polynomial, x cubed minus 3 times x squared minus 2 times x plus 6, and I'm going to give an initial guess, x equal 1. All these expressions usually require an initial guess because they rely on iterations. Guess and update in order to get to a solution. And then the root of f of x in terms of x. Okay, what are the values of x that make, that's what a root is, the values of x that make this expression 0. Now, because this is a cubic polynomial, there's a possibility that there's more than one solution. Usually a cubic polynomial will have 3 solutions. Sometimes a pair or many pairs of those solutions are not in the real domain. They are sometimes in the imaginary domain, so they would not appear to be a possibility. So if I do this, I find the solution 1.414. If I change the initial guess to 10, I find another solution, 3, which is also valid. If you replace x by 3, you'll find that these is made 0. How about if I use minus 10 for the initial guess? I find minus 1.414. So there are 3 solutions that are already identified. Minus 1.414, 1.414, and 3, depending on the initial guess. And the solutions depend on the initial guess because this is a numerical technique. There's an algorithm, and there's guessing and updating behind the solution of these simple cubic polynomial in terms of the roots. There's also the polyroots. I can give, for example, the coefficients of these polynomial of order 3, or any order for that matter, but let's just do it with these polynomial. A polynomial of order 3 will have 4 coefficients. So I'll give them in the form of a vector, starting with the independent term 6. The term that multiplies x is minus 2. The term that multiplies x squared is minus 3. You have to give it in that order, from independent term all the way down to, in this case, a cubic polynomial, with the term that multiplies x cubed being 1. and I can use polyroots of vector b, and it would automatically assume that there is a polynomial that has this coefficients, and obviously it knows it's a cubic polynomial because it has 4 coefficients, and the solutions are minus 1.1, minus 1.414, 1.414, and 3, which are exactly the ones that we found through the use of the roots function. Okay, depending obviously on the initial guess. All right, so you can use that roots function for more complicated functions that are not necessarily polynomials. You can use trigonometric functions, you can use exponential, logarithmic functions, rational or irrational functions, but the polyroots function or the polyroot statement only works for polynomials, and you give the coefficients of that polynomial directly on a vector. Now, to finish up, another numerical technique that MathCAD uses in the background is to solve definite integrals. So if I give an expression of the form, let's say I'm going to use the calculus toolbar, and I give an expression of the form, I want an integral from 1 to 2 of x cubed, or x squared, let's say, plus 2x minus 3. I want to integrate this quadratic polynomial between 1 and 2. How much is that? I use a regular display equal 2.333. Okay, there's no big deal with that one in particular because this is an integral that we can actually solve. It's a very simple integral. The integral of these is x cubed over 3 plus 2x over 2 plus 2x squared over 2 minus 3x. You evaluate it at 2. You evaluate it at 1. Subtract the 2 and you get 2.333. Okay, for those of you that are going through calculus 2 or that already know what integrals are, this is how it works. Now, the way MathCAD did it wasn't, and how it afforded to do it so quickly, it wasn't because it actually solved the integral. What MathCAD did was use certain numerical techniques, either trapezoidal summation or Romberg integration or Gaussian integration. Depending, you can actually select the type of integration that you want. And notice that if you right-click, you can actually do Romberg, adaptive, infinite limit, or singular endpoint type of integration to get to the answer. Now, the most impressive thing is the ability of MathCAD of giving you a solution for an integral that doesn't necessarily exist. So let's say that I want the integral from, let's say, 0 to 2 of e to the x squared. Now, this is an integral that's called the error function integral that you cannot solve analytically. This integral doesn't have an analytical solution. You try to solve this by parts, you try to solve this by trigonometric substitution, you try to solve this by convolution or any other type of substitution, you will not get to an answer. It's e to the x squared. Okay, that particular integral doesn't have a solution. But because analytically you cannot get a solution doesn't mean that you don't have a numerical answer for the solution. The integral from 0 to 2 of this curve actually exists. It's a smooth curve. Is a monotonically increasing curve from 0 to 2. We can always get the area under the curve, and MathCAD does that for you using numerical approximations, numerical techniques. And all you have to do is say this is equal to, and you get 16.453. Okay, you can do so with many other expressions. For example, an integral between, let's do a definite integral from 0 to 1 of the cotangent of x to the power of 2. Not x squared, but the entire cotangent squared dx. Okay, this is not a simple one either. Actually, try to find an analytical solution for these. And in this case, it didn't find an answer because this is an integral that has the cotangent is the cosine over the sine. So this is an integral that is improper, because when you evaluate this integral, when you evaluate the cotangent of 0, the cotangent of 0, you get a singularity. The cotangent of 0 is infinity. So there are things that you can do for these. You can do a limit. Let's integrate from 0.0001 to 1, and you actually get a solution that tends to infinity. As you approach 0, the solution will grow and will grow and will grow exponentially until it says well, I cannot do it anymore. But let's say you want to integrate the cosine hyperbolic square. The cosine hyperbolic square, the hyperbolic functions are actually exponential functions. So this will be almost the same case as this function that we try to solve over here. You do get a solution for that. There's no singularities or anything like that. Let's see if we can actually use a symbolic manipulator to get a solution for these integral, which I told you doesn't have an analytical solution. So if we actually use a symbolic manipulator, we'll be saying evaluate this. It actually found something, but notice how strange that solution is. It's square root of pi times ERF of minus 10i times I over 2. The solution of this integral actually exists in terms of an unknown function called the error function, which is, by the way, the error function is a function that is defined as the integral of e to the x squared. It's a function that didn't exist before somebody tried or attempted on solving this integral right here of e to the x squared. So this function, error function, is defined as the integral of e to the x squared. So it's kind of redundant. The solution, or the integral of e to the x squared, is the error function, but the error function is the integral of e to the x squared. So although it's redundant, the symbolic manipulator has the capability of actually digging through the databases and making decisions to get to the answer on these, and actually does a good job, and it expresses it in terms of the square root of pi over 2 instead of just giving you a number, the square root of pi over 2. So this is the class today, and we went over some very important features in MathCAD, very powerful features such as symbolic manipulators, symbolic operators, and we also looked at solve blocks and numerical techniques for using MathCAD. And as I said, and I've said for all the lessons prior to this one, we're only scratching the surface on this software package. There are many other very impressive features that you're going to find very, very useful as you progress in your engineering studies, and you're going to get back to MathCAD and get to use them a lot. So thank you very much for your attention, and I'll see you in future tutorials.